Oh, wow, there are actually a lot more hands than I thought. Good. So hopefully, if you were able to or inclined to, you got to take a look at my notes that I had online. Again, some of these questions I will do just as is. A lot of them will be very similar, but I'm going to change the numbers up just so you can see numbers or no, we have this down. And I think it was Martucci's going to be my random fast fingers on a calculator. If anyone else wants to also join him on being a calculator person, that'd be cool because I will be making up numbers, so I won't know the answers. Was that true, Martucci? Are you my calculator guy?
Yes, sir. I'm ready.
All right. All right, so what we're going to do is we are going to basically just solve a bunch of problems, learn how to set them up, learn what to look for, and just crank through, I don't know, probably like 10 to 12 of them and see how it's going. If we have time and people want more, I will try to do more as well. But let's just take a look. Remember, I'm going to go ahead and remind us of the equations that we have. So we'll do an equation reminder here. Equation reminder. And that is, we're going to be looking at using P1V1 over T1 equals P2V2 over T2. We'll later use PV equals nRT. We're going to want that 760 millimeters of mercury is equal to 1 atmosphere, and that the total pressure is equal to the sum of all the other pressures. So we're going to keep those in mind, and I'm actually going to be almost using those in the order that you see that, except for that 760 equals 1 atmosphere. That is going to be one that we're going to be using ubiquitously in these problems. Okay, so now that we're reminded of the 4 things we need to do this, let's go ahead and just jump into some problems. All right, I don't even know why I'm going to say example. I'm just going to start writing them out. Okay. A 7.12 liter sample of, I don't know, helium gas at 1,110 millimeters of mercury is going to suddenly expand. Suddenly expands to, I don't know, let's go 12.19 liters. What pressure caused this? Okay, so we have a balloon full of helium gas at a certain pressure, and it suddenly got bigger. What pressure caused this? Okay, so when I look at this problem, I start by asking myself, do conditions change or do they not? And so I will ask, do the conditions change for this balloon?
Yes, the pressure and the volume.
Yes. So if you take a look back at our equations that we have this guy right here, the P1 V1 over T1. Obviously, we're going from one set of conditions to another. We're going from 1 to 2. So this is good for changing conditions. This guy, we aren't going from one to another, and this is with, there's only one set of conditions. So by immediately asking the do the conditions change or not question, when we ask that question, If the answer is yes, we're immediately going to go to the P1 V1 over T1. If they aren't changing, we're going to go to PV equals nRT. So you did just tell me that the conditions are changing here. So I'm going to immediately write down P1 V1 over T1 is equal to P2 V2 over T2. And then I'm going to ask myself another question. Is there anything that is constant or was not talked about? Pressure, volume, temperature. Is there anything that we didn't even mention or said isn't changing?
T, temperature.
Right.
Temperature.
Yeah, no T. So we didn't talk about the temperature, so therefore we have to assume it didn't change. And if it's the same on both sides, guess what we get to do?
Dump it.
We get to dump it. And so now we're left with P1 V1 equals P2 V2. Now at this stage, what I like to do is go back up to that problem and start to pick it apart. And we got to think of some of our mathematical terms or grammatical terms in order to identify which of these pressures and volumes go with which. So here I have 7.12 liters. I'm going to go ahead and say that that is my V1. And then we have this word at, which means that volume is tied to this 1110 millimeters of mercury. So that must be the P1. And then of course I have this expanding too, which means I'm going to a different set of conditions. So that is now a V2. So I'm asking what pressure? That's what I'm looking for is the P2. So I'm going to solve for P2. And so that's going to be P2 is equal to P1 V1 over V2. Now, before we put anything in there, before we put any numbers in, I always like to solve these problems symbolically as much as possible. That avoids miswritings and mistypings and such. But even before I put the numbers in there, I want to ask you, do you think the pressure should go up or should it go down to make that balloon get bigger?
The pressure should go down.
The pressure should go down. So if we have done this problem correctly, at the end of this, our pressure should be less. Let's find out. So now we just plug it in. So P1 was 1110 millimeters of mercury. V1 was 7.12 liters. And V2 was 12.19 liters. Notice that our liters cancel out and we're left with a pressure like we want. And since I completely made this up, Martucci is going to tell me that that pressure is
648.33.
648.3.
Say it again.
648.3.
All right. Went down like expected. So whether you're 648.3 or 648, you know, you guys are going to have an answer there. It'll be the right one. So don't freak out about that. But in any of these problems that we are going to do, this is going to be sort of our mantra, our problem-solving strategy for calculating all this. And I'm going to go through all these steps nice and slowly. Of course, as you guys get much better about doing the homework and the things like that, you may end up skipping some steps and going straight to the end, and that's okay too. But again, I'm going to emphasize the problem-solving aspect of it. All right. If a sample, if a 517 milliliter sample of methane gas is compressed, from 1.85 atmospheres to 6.85 atmospheres, how big will it be? Okay. Bethania, are the conditions changing? All right, Fabian. Okay, then
Yeah.
April.
Yeah, conditions are changing.
Conditions are changing. All right. So if the conditions are changing, we should immediately be writing down P1 V1 over T1 is equal to P2 V2 over T2. Is
Yes.
there anything I haven't talked about?
Temperature.
Yeah. So that means I can get rid of it. And I can simplify it out as to P1 V1 equals P2 V2. Now, what is it we are looking for? Okay. I have up here an initial volume here of 517, so that's a V1.
Looking for volume.
We are looking for volume.
Mhm.
How big here? That's the V2. That's what we're looking for. This V1 is going from one to another. So there's your where you are and where you're going. So that's a P1 going to a P2. Right? So this 2 right here is telling you we're going to the other set of conditions. So we are looking for V2. So V2 is equal to P1 V1 over P2. Now again,
137.
so that we don't run into problems, but we compressed it. Is it going to get bigger or smaller?
Smaller.
Smaller.
Smaller. All right. So at the end of the day, hopefully our number is smaller. So we go back up to our conditions there. We have P1 at 1.85 atmospheres. V1 we said was 517 milliliters. And P2 was 6.85 atmospheres. Atmospheres cancel.
Shouldn't we convert milliliters to liters?
Aha. Ask that question in just a moment. I love that question. So V2 is probably 1/3 of that, so somewhere around the realm of about $1.50.
139.6 or 140.
140. I'll take 140.
Oh, yeah.
Okay. Now that's just me showing off the fact that I'm really good with numbers and see sort of the ratios.
0.1 leaf. Okay,
You don't have to be that fancy. You can just plug and chug it. I do encourage people though to do the estimations just like what I'm doing. I saw the 1.85 looked about like the number 2, 6.85, kind of like 6. So that's cutting everything in about 1/3. And I took 517 and cut it in about 1/3 and called it about 145. So I knew that my number was going to be in that neighborhood so that when I punch it in, it sort of makes sense in my brain. If you don't want to do that kind of extra work, that's totally fine. But for those who are, going on to be engineers and physicists and stuff like that, you want to start getting good at what's called the order of magnitude analysis, or what is sometimes called the back of the envelope, where you just sort of guesstimate where you should be so that you know you've done it right. Okay, Reagan, ask your question.
Shouldn't we convert milliliters to liters?
Why?
Because well, that's a good question actually, because I was thinking our calculation is in liters, although this was asked in milliliters, so maybe we keep it the same as what was asked.
That's right. Now, so when we're doing this, you'll notice it right now. So far, I don't care about the units insofar as if you notice the one above here, we were in millimeters of mercury in liters. Down here, we're in atmospheres and milliliters. As long as the units cancel, and I've been saying this since day one, since conversions on third week, second week, as long as your units work out, I don't care. Aside from getting from Kelvin to Celsius, that's the only one I care about. And the reason is so you measure the top one in millimeters of mercury and the bottom one in atmospheres. Who cares? The pressures will cancel themselves out. You were in milliliters before, you might as well stay in milliliters now, because why change the color of that? So right now you'll notice that I'm not being very meticulous about the specific nature of the units. I will later. And I'll point out why then. But right now, as long as your units are getting rid of each other and getting you to a value you want, who cares?
Got it.
So in the P1V1 over T1 problems, you don't care, because I'm not going to do something to you where I go like, okay, one of these is measured in atmospheres, the other one's measured in millimeters of mercury, and its volume was in milliliters. This one's going to be in gallons, and I'll do the temperature in degrees ranking, and the other one in Kelvin. Like, I'm not going to make you do that. The problems will stay self-consistent. And if you actually understood ranking, that's awesome on you. All right. Let's do another one. Is everyone doing okay so far? Is anybody like struggling?
Nope.
No? Should be pretty straightforward. I'm really hoping that this is a very straightforward way of looking at these questions. If you know you're having some trouble with the actual solving of these equations, stick around after the lecture, and I'll go through it with you guys some more and show you the steps for solving them. Otherwise, I'm just going to keep going forward. It's the Bushido code. Our only goal is to move forward. Okay. So a 15-liter balloon of hydrogen goes from one room to another. If the first room we're at, I don't know. Let's go 277 Kelvin. The other room the first room we're at that, and the other room, let's go with 312 Kelvin. How big will the balloon be? I've got a balloon, I'm going from one room to another. That other room is hotter. Is it going to get bigger or smaller?
When selecting
Bigger.
to protect against chemical exposure hazard.
Ooh, chemical exposure hazards. Easy. I don't know if everyone else heard that, but someone's getting some hazmat training. All right, so it should get bigger. We do see the conditions are changing. So we will go P1 V1 over T1 equals P2 V2 over T2. Is there anything we did not talk about?
Pressure.
Pressure, right? No pressure, get rid of it. So we now have V1 over T1 equals V2 over T2. We'll go back up to our equation here. Clearly the 15 liters is the first one, and we're going from one to another. So we're going from a T1 to a T2, and how big we're looking for that V2. So solve for V2. V2 is equal to V1 T2 over T1. We think it's going to get bigger? Let's find out. V1 was 15 liters. T2 was 312 Kelvin. T1 was 277 Kelvin. Kelvins cancel. We have our volume. And I'm going to be told that that volume is
16.9.
16.89.
Or
Six-
17.
Yeah, 16.9, 17, it's all good. 16.9 liters is totally fine. I'm not going to be worried so much about sig figs, especially because you'll have an answer there. But this is more about, can you do the job versus can you get sig figs?
Can you scroll down a little bit?
Like that or like that?
Like that, thank you. No, down, up, down.
Like,
Like to the answer, please, thank you.
sorry, I never understand.
I'm like, is your up not my up or?
You know, it's funny because when you say swipe up, it's like, do I physically want to swipe up, which means I'm going down the page?
Right.
That's not, I never understood the whole Tinder thing about swipe left or swipe right. Wait, am I swiping to the picture on the right, or am I swiping in the right direction, which means I'm actually going left? I don't understand this swiping thing. Give me a mouse. I want a mouse.
Can you mouse downwards, please? Thank you.
Well, scroll down and scroll up, I understand. All right. All right, just to show you that all of these temperatures are relative. Let's do another one. If a 12.8, oh no, you know what, let's do something bigger than that. Let's do a 750 milliliter sample.
Can I ask a quick question?
No, go ahead. Okay.
Will you always leave it in the same thing, or will you ask like change the, like one is a liter and the other one is a milliliter and you have to change it, or will you just keep them the same?
Keep them the same. I was
Keep them the
explaining
same.
my monologue after Reagan's question. I am not going to switch up these units on you. I'm going to keep them self-consistent in these changing condition ones. Converting from one set to another is not the aim of this. The aim of this is to quantify the physical change, the amount of the change. So there's no point in me going like, I'm going to switch up all the units and see if I can trip you up. That's not the point here. The
Okay,
point
so
is,
the temperature will always stay Kelvin or Fahrenheit, whatever you're using.
temperature, no. We'll talk about the temperature at the end of this question here. Temperature is the only one that you have to make sure is always in Kelvin.
Okay.
And I have an example of that. But the volume and the pressure, I will always be self-consistent within those. I will not give you two different sets of pressures or two different sets of volumes and try to trip you up that way. That's not the point of this.
Okay.
We'll talk temperature, however, at the end of this problem. Give me just a second. Sorry, it was very difficult for me to concentrate with my kid singing Love Shack in the background. And so I had to say, sorry guys, can you take it to the other room? But it is cute. All right. A 750 milliliter sample of nitrogen gas at 25 degrees Celsius. Let's make a better 5 there. Shrinks to, oh, I don't know, let's go 350 mils. How cold did it get? Once again,
Volume down, temp down.
volume down, temp down. Yeah, it should get colder. Yep. Now, I kind of telegraphed it when I said cold, so it is sort of telegraphing it, but I didn't want to say, what temperature did this, like your book will do. So let's go with P1 V1 over T1 equals P2 V2 over T2. Pro tip, for like the next 5 problems or so, the answer to do conditions change, the answer is yes. We'll get to where they don't change in a moment. All right, did I not talk about something?
Pressure.
Temperature, yeah.
No pressure. So let's get rid of it. Let's rewrite it as V1 over T1 equals V2 over T2. We come back up here. We have a volume that is at a temperature, and it's going to shrink 2. See, 2 means we're going to a different one. That's going to go to a V2. How cold? We're looking for T2. So we're going to solve for T2. So if we do that, T2 is equal to V2 T1 over V1. And again, we already think it should get colder, so our temperature should drop. And so now we're going to plug this in. So V2 was 350 milliliters. T1,
298.
298 Kelvin. And then we had 750 mils, I believe, was our original. Mils will cancel out. So T2 is equal to, let's see, that's about half of that. So 300, 150, maybe 140.
139.
Go ahead. 139 Kelvin. Now, since we don't think in terms of Kelvin, we should probably put that back into something that's somewhat more familiar. And let's do that to Celsius.
We
And
start,
that number is 273 away from that.
Yeah, 270. It's minus 133
Minus 133.
Celsius.
Okay. So let's readdress April's question and my answer. In these changing conditions problems, your pressure and volume, what you see is what you get. Temperature, that will always have to be in Kelvin. All right, so when we talk about doubling the temperature, we are talking about doubling the temperature in Kelvin. If you go the way back to the beginning of this lecture, I said things will be very mutable except for one, and that one is temperature. Temperature has to be in Kelvin. So, and by the way, I do want to point out that even though it's negative 133 C, we are nowhere near the point where nitrogen is going to become a liquid. Liquid nitrogen is 77 Kelvin, so we got plenty of wiggle room there. Nitrogen behaves for a long time. Okay, so why do we always convert? Okay. Oops. Let's get that back into purple. A 10.0 liter balloon is brought from inside the Antarctic Research Station to the outdoors. if the temp inside is 23 degrees Celsius and outside it is negative 40 degrees Celsius, how big will it be? One of my longer prompts. These are real numbers. So when we look at this problem, we know that it's changing. So we write P1 V1 over T1 equals P2 V2 over T2. We ask ourselves, is anything not talked about?
Sure.
No pressure, that's gone. So now we have V1 over T1 equals V2 over T2. We go back up here, and we look at our problem. We have a balloon that is V1 big, and it goes from a T1 to a T2. And of course, how big? We're looking for that V2, so we solve for V2. Okay, so now we have V2 is equal to V1 T2 over T1. We're going to do this two ways. I want to point out the wrong way. As I let you guys catch up on that writing, I should point out that that negative 40 Celsius is actually the same in Fahrenheit. It's the one point on the two temperature scales where they meet, negative 40. That was actually worth, I think, $500,000 on the Who Wants to Be a Millionaire game show. The person got it wrong. I was screaming at the television because I knew it. I could have retired like a king in Patagonia, but no, they wouldn't have me on there. You
Can
never
you
know.
scroll up just a bit, please?
Say what?
Can you scroll? There it is. Perfect.
Hey, Stuart's here. All right. How far behind are you there, Stuart?
All right, we're good.
We're good? Okay. Because I can stall. What I want to do here is I want to do this the wrong way. And that is, let's just say that I said V2 is equal to V1, 10.0 liters. T2 is negative 40 degrees Celsius, and T1 is 23 degrees Celsius. If you do that, you end up with negative 17.4 liters.
Wrong.
What does it mean to be a negative volume?
Can't be.
If your head didn't just explode thinking about what a negative volume is, you probably weren't thinking about it. It makes no sense. And so we cannot use Celsius, Fahrenheit, any of that to do this. We have to have a temperature scale that will not do that to us. So let's do it the right way. And that's going to be the V2 is equal still to our 10.0 liters, but we're going to take the negative 40 and turn it into Kelvin. So 233 Kelvin and our 296 Kelvin. Now we have our temperatures. Yes, the Celsius did go away, but it left us with something stupid. This one will now give us that it is 7.87 liters. Much better.
Horace, before you move on, can we go to the last one? I thought I did it right, but I didn't get the answer. So I'll wait till everyone's done this, but
That one?
yeah. I got 350, 298 divided by 750. Oh, you converted it back to, oh, I see what you did. You converted it back to Celsius.
Yes, and you'll want to do that because no one thinks in Kelvin. I've been doing this for 15 years and I still don't think in Kelvin except for the number 298. That's it. And maybe, what, 313 if you wanted to or not 313, it'd have to be two. No, you know what? I can't even think in that terms. I was trying to think of body temperature in Celsius or Kelvin, and I can't even do that.
Wait, so what was the answer? Sorry, you went so fast. What was the answer on that one?
What was the answer on what one?
The one that I just asked to go up and then you scrolled back down real quick. So you got negative 133. Okay, now I got it. Thank you.
Okay.
Yep.
Now, were you caught up on this one though, Reagan?
Yeah, that way, yeah, I stopped. Yeah, I moved ahead with you. I stayed with you. I just needed that one.
Okay. Okay, so that's why we always go to Kelvin, so we avoid those situations and we also avoid wrong answers. Even if the temperatures were not giving us something negative, doubling in Celsius is not the same as doubling in Kelvin. So want to make sure we're doing it the right way. All right, how about this?
Can you stop a bit? I have finished the first part. Please.
Which part? What do you need to do, Suman?
Yes, that's right. Thank you.
Okay. Guys, got to slow me down if I'm going fast. I get all excited about this because this is really one of those types of problems where as long as we just get in the zone, we're going to be good.
Question, sir.
All right, so we're good?
Question.
What?
Do we have to mention we convert in Kelvin when we do the math?
No, you're gonna click a button that says this is my answer.
Okay.
Yeah. Welcome to the world of multiple choice. Yay. The good part is your answer will be there somewhere. The bad part is 0 partial credit. That's the hard part. So don't screw up. I want you guys to do well. All right. A gas in a rigid container. Is originally at 3.15 atmospheres and 25 degrees Celsius. It is heated to 150 degrees Celsius. What is the pressure inside now?
Colton, no, you cannot have a popsicle. It's 10 o'clock.
I'm hungry.
He's hungry, feed him. Okay.
Excuse me, sir. I have a problem with the calculator on the top. Just scroll down a little bit. So you just check for V2, you make equal 10.0 liter times 233 Kelvin. And on the bottom, you have 296 Kelvin.
Yeah.
When I have the math for my calculator, it give me 250 Kelvin. Because 23 minus 273, it gives you 250.
You got to add 273.
You got to add?
Yeah. So the Kelvin is always bigger than Celsius.
Oh, wow. So I make a mistake over here. Thank you.
Mm-hmm. All right. So, Carissa, are conditions changing?
Yes.
Perfect. So of course, we're going to write P1 V1 over T1 equals P2 V2 over T2. Is there anything I didn't talk about?
Oh, volume. Volume.
Volume.
But I said it was rigid, so what does that mean? It's not changing.
Change.
So the volume is gone. So now we rewrite this as P1 over T1 equals P2 over T2. And we just take a look. What do we have? We have a pressure 1 at a temperature 1, and I change it to a temperature 2. I'm asking for that pressure. So I solve for P2. If I solve for P2, P2 is equal to P1 T2 over T1. Should my pressure be going up or down? Yes, it should be going up. We're heating it up. So hopefully we'll get a pressure that matches that. Otherwise, we're going to have a bad day. Okay. So that P1 is 3.15 atmospheres. T2, what is T2 going to be now?
423.
Say it again.
423.
423 Kelvin. Let's make
Yeah.
that better. Thank you. And of course, 25, I know that one is 298. Because we always have to get down to that Kelvin. And at the end of that, P2 is equal to
4.47.
5.47 atmospheres.
It's 4.47.
It's 4.47.
47, okay. Yeah, that makes a little more sense. Going from 300 to 400, you shouldn't mostly double. There we go.
This is 4.
Okay. Oh my gosh. Doing okay
So far.
so far. So again, I'm hoping that very soon, by the time I finish the next couple, you guys are going to be so bored with this because I will have shown you everything you can solve for. Hopefully, you'll be so bored with it, it doesn't matter. Like blah, blah, blah. I'm like, no, we'll actually move on to the easier ones after this. All right. Let's see. Oh, I was trying to see if there's anyone I could.
Can I scroll up? I missed the part. Yep, thank you. Oh, no, too far. Yeah, thank you.
Okay. Who do I want here? Martucci. Oh, no.
April.
Warnock. All right. All right. As punishment, we're using underage magic. Warnock's wand. Ooh. What's your wand made out of, Warnock?
Spruce wood and unicorn hair.
Spruce wood. Unicorn hair. Is vaporized.
Hey,
Hey, I'm sorry. You used underage magic, not me.
I'm
Is
19.
Put into a steel container. And breathed upon by a, Which was the really nasty dragon?
Hungarian horntail.
There you go. All right. Sorry. But you shouldn't have done it. All right. If the pressure and temperature were 298 torr and 30 degrees Celsius, the pressure skyrocketed to, oh, I don't know, let's go 1,786 torr.
This is giving me anxiety. There's too many words.
I'm doing this on purpose. How hot is the wand vapor now? I have now officially made, oh, I should probably do this. Hashtag hotter points. Shout out.
Yay.
There we go to Potter Points. Increase her traffic. She's a social media influencer.
We should get an extra credit point if we do.
What does it say after 298?
Torr, T-O-R-R.
Okay, thank you.
And I thank you for asking that question. Because I don't think I actually put it in last lecture, so I'm gonna have to put it in here. Okay, so while we do that, who asked that question?
I did.
Dear, oh man, can we get a little more enthusiasm there? All right, all right. Note. So we have units of pressure. There are many. We already have the atmosphere. We're pretty okay with that. We have the pounds per square inch. That's our PSI. We already had our millimeters of mercury. There's a few others that should be noted here. Others that we didn't talk about because I forgot to until today. There's also the torr and the bar. Think of barometer. But this guy torr, the Yadir is like, what is that word? Torr. This is from Torricelli. So the guy discovered pressure, figured out a way to quantify it. He measured it in terms of heights, but he also said, I'm gonna put my name on it. I'm gonna shorten it to torr. So torr is another unit of pressure. And I just want to point out that it doesn't matter what those units of pressure are here because they are going to cancel out. And that's okay. Like I said, I'm not going to give you mixed units there. I don't care if I gave it to you in some like completely weird. Pascals is another one for engineers. Pascals is a Newton over meter squared. As long as the units will cancel, you're going to be good, and they will in these circumstances. So, okay. We have this very long prompt that I did on purpose just to scare April and Reagan, so that I can make sure that you guys are never scared by a big, long word problem at all. Okay, here's how it's done. First things first, did we change the conditions?
Yes.
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 So we already know that we're going to say P1 V
P1.
over T1 equals P2 V2 over T2. Okay. Let's take a look at this. Is there anything I didn't talk about? We'll see.
Volume.
I got a pressure, temperature, I don't see any volume, right? Not only that, I even said it's a steel container, so it's probably not going to get any bigger or smaller. So the volume's going to stay the same. Look at this. It's already getting easier. P1 over T1 equals P2 over T2.
Can I ask a question?
Yeah.
So like in all of these, we didn't have something. Is there like, what about?
Walk with me, young Padawan. Walk with me.
Okay.
I'm doing this on purpose. Okay, so as we look at this, we go up here, and I just want to point out, this is for you, April. Ready? Does any of that matter?
No.
No, right? It's flavor for the problem. What does matter? You start at a pressure and a temperature. You start at a P1 and a T1, and you go to a P2, and you're asking how hot, so you're looking for T2. It's that easy. So when you look at these, quote, really long prompts, and oh my gosh, I'm getting scared because there's words. Why? Just enjoy the story and then get down to brass tacks. That's why I'm teaching you how to go through and look at the information that's given to you. Look at these words. Look at these words. And means we're going to get those things and stick them together. The word to is telling you we're going somewhere else. All the rest is just flavor. Okay, so we're solving for T2. T2 is equal to P2 T1 over P1. Should that temperature go up or down?
Oh, up.
Why does it go up?
Because as pressure goes up, temp goes up.
Right, or vice versa. The temperature is actually the leading, the pressure is the dependent on this, but that's okay. Your thinking is
11 o'clock.
What? No, that heard something. Okay, so we do think it should get hot, not to mention, it breathed upon by the Hungarian horntail. It is fire, so let's put it in here. So P2, 1786. T1,
303.
303. And P1,
298.
298. Okay.
1815.9.
1816 Kelvin.
Mm-hmm.
Okay.
Yes.
That seems normal. What is that in Celsius? Minus 273.
1543 degrees Celsius.
Oh, God.
Oh, man. We're almost to the melting point of steel. We're at least at the annealing temperature. So that's good. Container is holding. Yeah, stay out of the way of that breath. Okay, so since I think I already broke the record for my longest prompt ever with this guy, the next one will be long, but not too terrible. First of all, is everyone okay? Do I need to scroll up a little bit?
I think we're fine.
Okay. Sume? You still
I'm
there?
okay. I'm okay. Thank you.
Okay, good. All right. Forest plans on going to Lake Tahoe when this quarantine ends. He is going to take a balloon to his one and only friend. If it is 37 degrees Celsius and 772 millimeters of mercury here in Napa, but it is 20 degrees Celsius and 735 millimeters of mercury in Tahoe. How big will the balloon be? Okay. Massively long prompt. April's freaking out, having an anxiety attack. Reagan's doing the same. Sume is just going like, whatever. There we go. That's what you do. Especially because you can do that now. You're not in a classroom. You can freak out and you can do whatever you want. So just go, and then remember, this is just a blah, 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 blah. Oh, here's some numbers. So April, since you're so brave enough to share your hopes and dreams and fears, we will make this a safe for you to do so. Help me out. Are conditions changing here?
Yes, because you're leaving and going somewhere.
There you
Right.
go. So we have P1 V1 over T1 is equal to P2 V2 over T2.
Mm-hmm.
Ooh, hold on. I forgot to tell you how big that balloon was, right?
Right, we don't have volume.
A 5-liter balloon. Sorry. Glass is good for up close. Notes are far away. Oops. April, is there anything we did not talk about?
No, we talked about all of it.
That's right. We are changing everything. So we can't just get rid of something.
Okay.
Okay, so let's take a look at this. I have a 5-liter balloon. I'm going to label that as,
Volume 1.
okay, and it is at a T1 and a P1.
Mm-hmm.
The but means we're moving. So that means we have a T2 and a P2. I want to know how big it is going to be.
Okay.
So I'm going to solve for V2. if I do that, it is P1 V1 T2 over P2 T1.
Okay.
So V2. Our P1 was 772. Yes.
You put twice P2, 712 and 735 equal P2, P2.
Oh, sorry. You're correct. What? How did I do that? Sorry. Thank you.
Okay.
Sorry, it's T1 and P1. There we go. So we have our P1 of 772. We have our V1 of 5 liters. We have our T2, which is 20 Celsius, which is what, 293, I think? All over P2, which is 735 millimeters. And T1, which is, I think, 310. Now, before we actually calculate that, before we actually get that number, are we going to get bigger or smaller? Take a guess.
Bigger.
Smaller.
All right, we have bigger and smaller. April, why do you think it should get bigger?
Oh, well, because you were going to Tahoe, things get bigger when you're going to Tahoe.
I mean, let's face it, part of the prompt tells you, okay, maybe it should get bigger. Now the pressure has dropped.
The pressure has dropped. The temperature is dropping too.
Right, but see, Winnie said the temperature is dropping.
Yeah.
So April says the pressure dropped, that balloon should get bigger. Well, Winnie said it got colder, so it should get smaller. Now, when you don't have a variable that you can throw out, when you have all of them in play, unless they both are doing exactly the same thing, you don't know, right? If they were both telling you it's getting bigger, then obviously you're going to get bigger. If both indicators are saying it should get smaller, it'll get smaller. But here we have a competitive effect. Pressure says I'm going to get bigger. Temperature says I'm going to get smaller. The question is, who is going to win at the end of this day? And Martucci is going to tell me, because I don't know the answer, because I made it all up.
4.96.
4.96 liters.
Yeah, see, I didn't get that. I gotta redo it.
I know.
I got it.
What you got was something probably ridiculously big.
Yeah, 477,011.9728.
And I get, here's how you probably did it. You went 772 times 5 times 293 divided by 735 times 310.
Yeah.
You should divide it by 735 divided by 310. And tell me if you get it. That is a common mistake, is to accidentally multiply at the end of all that.
So divide one time by 735 and get the answer, and then divide again by 310.
Yep.
Okay. Yeah. 4.96.
Yeah. And we can, after lecture, we can discuss some calculator strategies if you want to also help you.
Okay.
Okay.
So can you repeat the way to make the math again? Because when I plugged my machine, it gave me a wrong answer.
Okay, we're going to work on your machine after class.
Okay. No, the process to plug the numbers on this calculator.
I'll teach you after class.
Okay.
Well, we'll have a contingent of people. All right, here we go. If a sample of oxygen gas is 5.85 liters at 1.75 atmospheres and 40 degrees Celsius, How many grams of oxygen is this? All right, Carissa, since you made the mistake of actually participating when I called on you, I'm going to do it again. Are conditions changing?
Yes.
What's changing?
The mass.
Oh, what's the one thing that can never change, folks?
Us.
Mass
Folks,
constant.
nothing is changing.
Nothing's changing.
There you go.
Mass can never change, right? That's why you're saying it.
Well, do I see two temperatures?
No, just one.
Two pressures.
No,
Do I see two volumes?
no.
I only have one of each.
I wanted, yeah,
No changing conditions.
got it. Okay, good.
No change in volume, temperature, or pressure. So if there's no changing conditions here, we are not using the P1 V1 over T1. We are using,
PV equals nRT.
there you go. Now it should be noted that when we're doing this, pressure has to be in atmospheres. Volume has to be in liters. Temperature, of course, is Kelvin and is in moles because R is 0.08206 liters times atmospheres over moles Kelvin. And that's why these have to be in those units. If I give them to you in something else, you better convert it. While we were able to use whatever units we had in the other gas laws, commonly called the combined gas law, because we're combining all the different ones that people had. In the ideal gas law, we have to stay in these units. Okay. In this problem, we clearly have
Second, so is that liters times ATM? That's the thing we're gonna use.
yes. I think I understand that question. So we'll keep going and we'll see if I answer your question. So if we go back there to the top, we see the volume, the pressure, and the temperature. And I say how many grams, okay? But what do grams also look like?
Moles.
Moles.
Right. So when we take a look at this, we have pressure, volume, temperature. We already know R. We're going to be solving for N and then converting it. So N is equal to PV over RT. That pressure was 1.75 atmospheres. The volume was 585. R is 0.08206 liters atmospheres over mole Kelvin. And I think we were at 40 C, which is 313.
That is 0.406.
0.406 at the end.
Yeah. Moles.
Wait, so we just basically are crossing out mole, that equation down the bottom.
Atmospheres, gone. Liters, gone.
Gone.
Kelvin, gone. And oh, look, there's the units we want.
Wow.
I got 0.399.
399? Okay.
Oh, impressive.
Really?
Really? I trust the Martucci.
Divide by.
Okay. At the end of the day, though, that's not what we wanted. We wanted the grams. So I know that 1 mole of oxygen.
Really?
Really?
No, I'm looking at his answer.
I thought I heard someone else back up Martucci when he did it.
Yeah, I got that as well.
Yeah, I got that.
Okay. Good.
Oh, look, so did I. Stay after class, Whitney. We'll figure it out. Now, this last step, hopefully you guys are okay with what I did.
I got it.
Right, I went to the periodic table. Oxygen weighs 16, but it's a diatomic, so it must be 32. At the end of that, that means that the grams are how many grams? Probably close to
16.
14.4. What do we got?
I
Oh,
got
six-
12.73 for grams.
12.73.
I agree.
7.
I like how Martucci. I'll allow this. I agree. Okay. So what we have there is a very simple PV equals nRT. That's almost about as hard as it gets. Let's do one more. If we can go that way, we can go the other way.
I got 12.3. Oh, no, I got 12.76.
A standard road bike tire can be filled with 14.0 grams of carbon dioxide to a pressure of 110 psi at 77 degrees Fahrenheit. How big, or actually I'm going to say, what is the volume of this tire?
Okay, so nothing's changing.
Oh, alrighty. Reagan said nothing's changing.
Now I'm just getting real, real confident of myself. So we're solving for volume. So volume is equal to nRT over P.
All right.
So now I'm going to do V is equal to,
We need the N, right?
I need the N, and if that's moles, then I would take I have to take my 14 grams.
Uh-huh.
CO2, yeah.
And that weighs 44.01 grams. And since we went to the periodic table, that's only 1 mole. The gas constant, 0.08206 liters times atmospheres over mole Kelvin. That's totally fine. By the way, I will give you that number on the exam. You don't have to memorize it. By the way, I will give you that constant on the exam. You don't have to memorize it.
Thank you, Mr. Constant.
Real quick, are you going to do this first parentheses as one and then get the number and times it by this next one?
However you want to do your math is however you want to do it.
Okay.
I went ahead and did it as one calculation because I'm the awesome that way. What's this temperature going to be?
71 plus 4. Oh shit, this is Fahrenheit.
Don't worry, I'm not going to be that much of a jerk to you. That's 298 Kelvin, and this PSI is 7.5 atmospheres. So I won't do that to you, but I just want to point out that we didn't have the correct units. So we have to make sure we had it in the right units. 298 Kelvin and 7.5 atmospheres. I decided for the few of us that have actually ridden the bicycle, you know you have to pump up your tires to 110 PSI, and 77 is room temperature in science. So, Martucci, please tell me you got something in the neighborhood of 1 liter.
Screw up a bit, please.
1.04.
Yeah, that's what I got.
Good, because that's what I have. I was only asking because in mine, I kept it 7.48, so I wasn't sure if it were going to change the 4 to a 3 or not. Now, I do want to point out that this is a real life problem. You can buy those little CO2 cartridges at bicycle stores. So if you're changing a flat on the side of the road, and you put your new tube on, you just take this cartridge, you push it on your valve, and boom, your tire just inflates perfectly to the exact amount. I was always amazed that when I would look at those cartridges, they would say 14 grams of CO2, and I'm like, why are you doing that? Why would you sell me a mass of gas? And then it dawned on me, because what they're going to assume is that you're at nominal temperatures and you want to get it to this pressure. This is how much gas would fit in there. And I said, but how do they know? Well, I actually took my bicycle wheel and I measured out its 2 diameters, the inner and outer, and said, bam, calculated the volume difference and went, oh, that's why, because it actually is about 1 liter's worth of gas inside of a road bike tire. I was like, oh, that's just too clever. So I turned it into a problem, a real life problem.
I'm confused because we were dealing with grams and then you went to a liter at the end.
No, I didn't.
So 1 mole over 44.01 grams. Oh, because the gram.
Because I asked how big. I asked what's the volume, right?
Yeah.
So,
Yeah.
so let's take a look at this real quick. We have this grams. We know that this is moles.
Yeah, I got you now.
And we have the pressure and we have the temperature. I'm asking for the volume. And so
Sorry.
look, you got your grams top to bottom, your moles top to bottom, your temperature top to bottom, and your atmosphere is canceled out, and you're left with your volume. That's as hard as it gets, guys. That one, with the PV equals nRT, those are like plug and chugs.
Do you think you'll do tricky stuff? Like I just said, I'm
not gonna do anything like that. The closest to tricky you're gonna have is Celsius to Kelvin. I'm not going to do the 110 PSI and the 77 Fahrenheit. That's not the point. You just have to make sure that in these problems, though, if the pressure were given to you in millimeters of mercury, you would have to go to atmospheres. I expect you to know the 760 to make an atmosphere. If I gave it to you in milliliters, you'd have to change it to volume in liters to make sure everything canceled. But I'm not going to do any like English to metric on you. But changing from milliliters to liters in Celsius to Kelvin, that's fair game.
Okay.
Again, I don't want to make this a difficult test. I'd like to give you guys something that bolsters your grade, as it were, before you hit that final.
Woo! Yes!
What did he say? I missed that. What'd you say?
I just bought your love by trying to give you guys an easy enough exam that you get a good score to go into the final, a little bolstered.
Woohoo!
Oh, thanks. Do you know how many questions are going to be? Oh, you know what? I don't care. Never mind. Doesn't matter.
Thank you.
Don't just stress me out.
Yeah, don't get. Yeah, I'm not answering your question, Reagan. It's just
Okay.
stress ball. All right. The one we haven't talked about.
Yeah.
Vapor pressure. This is the easiest of all of the problems. Vapor pressure. Martucci, when I say the words vapor pressure, what does that mean? Oh, is he gone?
Total pressure.
Okay. Vince is there. He's just drinking a Red Bull. Yeah, it has to do with total pressure. But vapor pressure, if you go back to the intermolecular forces that we talked about a few weeks ago, this is the pressure of a vapor, and here's the kick, over its liquid.
Partial pressure.
Yeah, it's also called partial pressure. Now, but the partial pressure is slightly different because that could be the summation of things that don't have liquids around. Say, for instance, if you're just talking about air with nitrogen and oxygen, 79% of the pressure is due to nitrogen, the other 21 is due to oxygen. Those would be called partial pressures. Vapor pressure is a little bit different, and that is because you want to have that liquid around to get that vapor into the atmosphere. But the two can be used essentially interchangeably. They can be used interchangeably. It's just vapor pressure is talking about how much of that stuff is there, and it's got to come from somewhere. Now, for instance, if you think about this, you know, think humidity, right? You need water nearby to be humid. So here in the Napa region, we are actually really close to the bay, really close to the river. We have a lot of water around to make sure that we have a decent amount of humidity. Every time I go to visit family back in Bakersfield, there ain't no water there. It's a dry heat. And my sinuses dry out like nothing because there's no vapor pressure of water around. There's basically nothing in the air, and it just dries you out. Coastal cities are humid. Deserts are dry. There's no water in the desert. So you need that liquid around to put that pressure of itself into the atmosphere. It's always a hot, humid day. It's never a cold, humid day. That's another thing too. Now, what this really means though, is that all the gases that are around, oops, contribute to the overall pressure. And this is where we have that total pressure is equal to the summation of all of the other pressures, P1 plus P2 plus P3, for however many gases you have. Parts equal the whole. So, I mean, this is, if the atmospheric pressure is due to oxygen, nitrogen, argon, and water vapor, what is the pressure of H2O if the pressure of oxygen is 152 torr, the pressure of nitrogen is 494 torr, pressure of the atmosphere is 760 torr, and the pressure of the argon is 1 torr. Now, as you write that down, I hope that you guys see a little coincidence. It's not a coincidence that the atmospheric pressure I said was 760 torr. Looks a lot like the atmospheric pressure being 760 millimeters of mercury. So it should be noted that this guy right here one torr is equal to 1 millimeter of mercury. Nice little how do you do. Let me make sure that that's not going to misdo. So it's inconsequential for this because since everything's on the same units, it doesn't matter. But we know that the pressure of the atmosphere is equal to the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the argon plus the pressure of the water. We wanted the pressure of the water, so that's the atmospheric pressures minus the nitrogen, minus the oxygen, and minus the argon. So it'd be 760 minus 494 minus 152 minus 1, and these are all torr. If you get that, I think it's 113 torr. Pretty humid day. That's as hard as it gets, guys. That's as hard as that gets. All right. Preguntas?
Can you go up a little bit on the page, please?
Can do.
Thank you.
If there are no other like burning questions like that, I'm done with everything you need for the exam. That's all we're gonna do. And so I can stop recording and then answer like calculator questions and that on the back end, unless there are some burning questions. There's something in the chat. What is this?
Can you scroll down, please?
Can I scroll down, please? Yes.
Thank you.
Somebody said something in the chat. I'm trying to, what was this about? 12 point, where's the 12.768? 398? April, are your questions about that 12.768 already answered?
Yeah, that was a long time ago. That's when everybody was kind of getting a little bit different answers.
Okay.
And
Yeah,
there was 12 point something, 12.4 or something like that. And I'm like, well, I got 12.7. I mean, close enough though. Like, it'll be one of the answers.
Yeah, that won't affect it. All right, I'm about ready to stop recording.